Welcome everyone, my name is George. Today I'm going to talk about what has happened in PipeWire during this last 1 year. This last year, 2020, was arguably not the best year, but for PipeWire it was a really good one. And this is actually something that you can immediately see by looking at the release history of the past 1 year, starting from February 2020, when we released version 0.30. It was the first API stable release supporting audio and a couple of other things, changes compared to the previous versions. And since then we had 23 releases up to the day of recording this presentation. It was almost one release per month. Some months had even 2 releases or 3 releases, and a lot of things changed during this past year. So PipeWire is today, it's very different than it was 1 year ago. Now, looking at WirePlumber, the session manager that myself and my team have been writing, WirePlumber had a less interesting year, but still we focused a lot on desktop support, starting a little bit before the summer of 2020, following changes that were happening in PipeWire Media Session and are still happening. So we keep track of what happens in Media Session and we provide equivalent functionality. We improved a lot our internal mechanisms, internal code. Introduced Lua scripting support, replacing the previous TOML configuration mechanism. Lua scripting support basically allows us to implement configuration of policy and a lot of other things, writing simple Lua scripts with a few lines of code, and it also allows us to write some standalone executable Lua scripts that do stuff in the PipeWire graph for easy prototyping and testing. Now the next release is going to be 0.4. It's expected to be released this spring. And we are targeting to replace Media Session before the end of the year. PipeWire, as you know, is a project that aims to provide a universal multimedia bus for all systems. And one of the goals is to replace the Pulse audio daemon. So let's look at how PipeWire did at replacing Pulse Audio this past 1 year. It started out really experimental, but until fall 2020 we had some good support that was pushed out experimental to Fedora 33, and now it's going to be the default, so it's going to replace Pulse Audio in Fedora 34, the next release, or so I've been told at least. It's mature for daily use. It provides most of the features of Pulse Audio. For 95% of the people, if they don't know that they are running PipeWire, they won't notice the difference. There's nothing that tells that this is PipeWire and not Pulse Audio. It is implemented using a Pulse Audio compatible socket. So there is a Unix domain socket that speaks the Pulse Audio protocol, and there is a daemon behind that socket that translates the Pulse Audio protocol to PipeWire protocol. Before that, that was added in fall 2020, I think. Before that, we used to have a replacement libpulse library that intercepted the API calls from applications. But this mechanism didn't work as well as the replacement socket does, and it was also problematic for sandboxed applications like Flatpak applications that were coming bundled with the libpulse library, and we couldn't replace that libpulse library in there. So now we provide this socket. It works much better actually, and it has also one more advantage, that it allows us to implement pulse audio over TCP, so networking, pulse audio networking support is also there, because it's effectively just pulse audio commands over a TCP socket instead of a Unix domain socket. And if you look at the terminal, as you can see, this is a screenshot from my terminal on my desktop. Pulse audio is not running, PipeWire is running, and we have this PipeWire pulse daemon running there behind the scenes. That is implementing the translation layer between pulse audio and PipeWire. And yeah, native pulse audio tools like PA they don't notice the difference. You can only tell that it's PipeWire because of the server name string that says PipeWire. In order to provide good pulse audio support, of course, PipeWire had to also implement card profiles. This is one big thing that pulse audio does. It configures cards with user-friendly profiles like stereo analog or HDMI audio and things like that. And you can switch between those easily. Now this is something that pulse audio used to implement with its own mechanism. This mechanism was basically pulled out of pulse audio back in June, as far as I remember, and it's now provided as a standalone library. It's called the ACP library. ACP stands for ALSA card profile, which is exactly, it's the mechanism that provides these card profiles pulled out of pulse audio and can be used standalone. So we can now provide the same card profiles using the same configuration files that pulse audio had, providing exactly the same profiles with PipeWire. And ACP also has internally, it has also UCM support. So if a card has a ALSA use case manager configuration files, then it is able to use the profiles from UCM instead of generating its own ALSA card profiles. So this is also available now, and it's possible for any card now in PipeWire to switch between using ACP profiles, UCM profiles, or just expose plain PCM devices. So it's flexible, versatile, and the code is shared with pulse audio. Now, enabling ACP and UCM, which is the default for desktop at least, gives a seamless experience for pulse audio users. So if you look at PAVU control, the native pulse audio volume control application, it looks really the same as it does with pulse audio. So you have output devices looking the same, with the same names even. Input devices, again the same, with device monitors as well. And card profiles appearing in the configuration tab, and you can switch profiles from there. And playback clients, of course, appear the same, and there is the ability to select which output device they are outputting to from there. So you can select the device and change that at runtime, just like it happens with pulse audio. Now, another thing that PipeWire has been trying to do is to replace the Jack audio daemon, which is an audio daemon meant for professional audio applications. PipeWire was inspired a lot by Jack, so they look kind of the same internally, only that PipeWire is able to provide to accommodate more use cases, so it can implement also pulse audio use cases. For replacing Jack, the status also changed during 2020. it started out as something that mostly worked. Since this year has been a year of so much testing, a lot of new users started using PipeWire, and they started testing and trying to port their previous setups of professional audio to use PipeWire, and a lot of bugs were fixed. So today it's really mature for most use cases. There are a few use cases that are still not addressed, and maybe they will be addressed in the future, but yeah, for most things it is a stable jack replacement. Now, the jack replacement is implemented using a replacement library, as it was the case with Pulse Audio before, but Pulse Audio switched. The jack implementation has not switched, and it is not expected to switch at all. It is easier to implement the jack replacement with a library because it is the two APIs are very close together. There is a PipeWire jack tool available. It is basically a wrapper around applications that switches the LD library path for being able to install both the original jack libraries and the PipeWire jack libraries if you wish to. And for cards, apart from the standard profiles that ACP provides, we now have also a Pro Audio profile, so you can change to a Pro Audio profile, and that will make all the available devices appear from a card. And this is something that Pro Audio users expect from their devices to be all available there, not to have to switch profiles. So it is more suitable for Pro Audio use cases, this profile. We have metadata support. We support writing jack metadata in the server and retrieving them. We have MIDI support, so all MIDI devices also can appear. MIDI applications can be scheduled through the graph, and yeah, of course, all the scheduling is real time with dynamic latencies being able to be configured. When we say dynamic latencies here, yeah, the latency can change at runtime, but it can change when other applications are added in the graph. The graph basically tries to, every application basically tries to request a single latency latency, its preferred latency and then the graph is scheduled so that it accommodates this requested latency for every application. So if we have applications with different latencies mixed up, then the whole graph will run at the lowest latency, and applications that expect higher latency will be buffered. And you can see from screenshots, Qjack control, for example, is a jack control tool, and it has a graph visualization where you can see all the devices and applications that appear there. And you can see in this screenshot, for example, that we have Firefox appearing there. Firefox is a native Pulse Audio application connecting to PipeWire and appearing as if it was a jack application for Qjack control, which is a jack application. And some interesting stuff that we can do now is we can mix Pulse Audio and jack applications in the same graph and make them work together. So here I have a Calf Studio Gear, which is a jack native filter application talking to Firefox, which is a Pulse Audio application, and they communicate through PipeWire. So the sound from Firefox is going through a real-time filter, and then it goes to the device. All configurable through the jack session, the jack patch bay here. Now let's look at something else. Let's look at performance. PipeWire performance also has improved this last year, and we even got tools to measure performance like PipeWire Top and PipeWire Profiler, which are available now in the latest version. There have been some measurements also available in the wiki that show that it outperforms Pulse Audio by far, and outperforms Jack as well, marginally, but still. And here I have some data taken from the wiki. So here we have PipeWire and Pulse Audio playing a single 16-bit file, 2 channels, 44K, and this is on a Core i7 processor, 4th generation. We can see here comparing similar periods. Periods are measured in samples, so for 1024 samples per period, we have here, you can see that we have, let's say, 430 context switches on PipeWire server, and 6.8 million instructions executed on the PipeWire server, while on the Pulse Audio server, for the equivalent scenario at the same period, so the same latency, we have 4,800 context switches and 183 million instructions. That's not even comparable. We're talking about 10 times more context switches, about 30 times more instructions, and yeah, CPU time is also affected, of course. It's not comparable. PipeWire is clearly much faster. In this second slide, I have PipeWire and Pulse Audio again, doing mixing of 2 files being played back. These 2 files are different, so one is 44K, the other is 48K. The one is 16-bit, the other is 24-bit. And they are being played together to the same device, so effectively the server converts these files, resamples them, and converts their format to match the device. And this is done before mixing. And you can see again here that measurements are not comparable. Context switches, instructions, CPU time on the PipeWire side, they are about the same as they were before. While in Pulse Audio, they are again same as before, almost, they are a bit more, but not comparable. The Pulse Audio is not doing good at performance here. And then a final slide where I compare Jack to PipeWire. The table at the top is PipeWire, the table at the bottom is Jack. Jack is running in synchronous mode. Synchronous mode is very similar to how PipeWire schedules the graph. And you can see here that these numbers are very close. About the same amount of context switches, about the same amount of instructions executed, but still every single number on the PipeWire table is smaller than the equivalent numbers on the Jack table. So we can see that PipeWire still outperforms Jack by just a little bit. And now let's talk about another big thing that happened in 2020. So in 2020 we got so much better Bluetooth support in PipeWire. And let me tell you the story behind that. So Bluetooth started in 2018 with Wim Tymans, the original author of PipeWire, adding support for A2DP sync. His use case was to be able to play music through a Bluetooth speaker. That sort of worked. Now, as part of our work for AGL in 2019, my colleague Julian added support for A2DP source and hands-free profile, headset profile, HSP. That that support did not work great at the time, especially the HSP support was problematic. It worked for Julian, but it didn't work for everyone. It was a bit more complicated than we thought. Anyway, that was not finished at the time, but later on in summer 2020, as part of Collabora's R&D, another colleague of mine, Kiagiadakis, who is an expert in Bluetooth, he implemented support for Ophono and HSP-HFPD, which are both daemons that implement the HSP and HFP profiles. He also added support for the MSBC codec for when using HSP-HFPD. And that was actually working well at the time. However, A2DP was not working at the time. It was broken because of changes that had happened in the PipeWire API in the meantime. So later on in November 2020, Wim fixed A2DP support, made it usable again. And then a little bit later, December 1st, there was the beginning of a breakthrough that started with some developer conflict in the Pulse Audio project. So the Pulse Audio, there was a merge request for Pulse Audio adding HSP-HFPD support that was closed because of some developer conflict. And there were a lot of people that were watching this because they were interested in HFP support on Linux. They got angry with Pulse Audio and they switched to PipeWire at the time. And they switched for a simple reason, because we had added HFP-HSPD support a few months before and it was working. So they saw something that was working there and they switched. And that initiated a huge wave of volunteers that assisted the PipeWire effort. They started testing, they provided bug reports about things that were broken, and some of them even contributed code. And a lot of issues that existed at the time were also fixed. Also, Wim added A2DP codec support shortly after, so maybe 10 days later after this started, the Bluetooth frenzy started, he added a codec support, so we got nice support for encoded streams. And in parallel, my colleague Frederick was still working on HSP and HFP, and he was writing support for a native backend for HSP and HFP. Native backend basically means that this backend doesn't require an external daemon like Ophono or HSP-HFPD. It runs completely internally in PipeWire, and I was merged later on in January, and that leaves us with a state-of-the-art Bluetooth audio implementation for Linux that started back in 2018. And progressed a lot with our work for AGL and later on Collabora R&D, and of course all these volunteers that switched from Pulse Audio and helped test the support for Bluetooth and make this a real thing. Nowadays I use it daily. My headphones, Bluetooth headphones, I use them daily with PipeWire, both using A2DP and HFP, and they work really nice. I do most of my conference calls with these headphones now. There is really no issue. So what lies ahead? So first of all, one of the major things that we're going to address during the next months is to integrate WirePlumber in mainstream PipeWire, and see how we can also do advanced policies on the desktop. This is more of a design issue and not a technical issue. We don't know exactly how things like multimedia streams and notification streams are going to blend together if we mark them as such on a desktop. We know how that works on automotive or on mobiles, but we don't know how that would work on a desktop. So it's something that we could look at. And of course, the compatibility race is still on. We need to make sure that every Pulse Audio and Jack application works. And especially for Jack, there are things that, as I said earlier, are not implemented yet, so this is something to be added. We are looking at advancing the video bus use cases. So PipeWire is also, apart from audio daemon, is also a video daemon. So addressing use cases of screen sharing, video camera input and things like that are also being looked at. Also, integration with lip camera is something to consider. We added some experimental lip camera backend in PipeWire also in summer 2020. But yeah, it needs more work to make it a real thing. More functionality for embedded use cases from both on PipeWire and WirePlumber, and a lot of other things that are mentioned in the wiki, in the to-do list, if you're interested in more technical details. That was all. Thank you for attending this talk, and let me know your questions.